shed, there are many different structural elements that can be used and considered. The first being columns. A column is a structural element that transmits through compression the load of the structure to the foundation and the elements below. Beams work in conjunction with other structural elements, and their purpose is to resist the loads applied horizontally to the axis of the beam. Beams are supported by columns and in some circumstances are supported by other beams. The main structural element that the columns and beams support are the rafters, purlins, bracing and sheeting of the roof structure. A rafter is a sloped structural component that is used to support the roof decking and associated loads. They are most commonly C-sections that vary in size and are joined together at the ridge with an apex connection and at the column with a knee connection. Fixed to the rafters are purlins. These members are horizontal structural members that run parallel along the rafters. These provide a base to which the roof sheeting can be fixed to. Furthermore, adding to the strength of the roof is a bracing. This is commonly known as speed bracing, is pre-tension and can be either applied in an X or V pattern. Purpose for bracing is to prevent buckling and rotation of the rafters under the weight of the roof, wind uplift, and some cases ceiling material. Following the bracing, roofing is fixed to the purlins, and in most cases the typical roof sheeting used is live-site trim deck. This is because the sheets are lightweight and provide increased wind resistance when compared to other roofing materials. Supporting the sheeting on the walls of the structure is a girt. Along with wall bracing, these girts give lateral support to the wall panel to aid in reducing wind loads. Portal-frame designs are common as they allow for large unobscured space as opposed to other designs which require different types of bracing and support. A portal frame contains three main connections, and they include apex, knee and base connections. An apex connection is used to join the rafters, and these connections transfer the bending moment from the roof to the base. These beams consist of two beams spliced with bolted end plates with optional haunches. A knee joint is used to connect the rafters to the columns and must be strong as they support the roof loads and must also prevent bending, and in some cases haunches are used as they reduce the depth of the rafter. The final main connection is the base connection, which consists of a single plate welded to the end of that column and attached with four holding down bolts. The bolts are fitted with anchor plates and are cast into the concrete to prevent pull-out. When designing concrete, it is important that you achieve the correct ratio of water to cement, sand and aggregate, as if an incorrect ratio is mixed, then it can result in a failure if the mix is watered down too much or there is not enough. This is why it is important that the slump test takes place, as the slump test is a means of assessing the consistency of fresh concrete. All these tests are carried out under Australian Standards 1379. Once the concrete has been mixed and is ready to be poured, the next step is to place the concrete in a metal cylinder, ensuring that it is filled to the top with no voids. When the cylinder is removed, the slump can then be determined.
For the columns of our shed, we determine the live and dead load forces placed upon the structure to determine the most suitable column. The first step we took was accumulating the data from the wind bracing, ceiling system weight, cladding material weight and the weight of the rafter. The column needs to be able to withstand the loads to transfer the weight into the footing. Once we collected the load weights, we calculated the total dead load of 52.208 kilonewtons. To determine the live load, we need to find the uniformly distributed actions. This is done by using the AS 1170.1 2003 table 3.2 other roofs. The formula from the standard used is 1.8 divided by A plus 0.12 kPa. Inserting the shed measurements in the equation, we are able to determine the total live load. 1.8 times 6 times 6 divided by 2 plus 0.12 equals 32.53 kilonewtons total live load. The live load will not cause a bending moment, as the connection between the rafter and column is a pin connection. The next step was to determine the wind load placed on the structure from the external walls. We obtained the data collected from the bracing design, which allows us to determine the total wind load for pressure and suction. We multiply the load by the span of our shed of a total of 6 metres. Total wind load pressure equals 2.088 times 6, which equals 12.528 kilonewtons per metre. The total wind load for suction equals negative 1.7864 times 6 equals negative 10.7184 kilonewtons per metre. Determining the load combination will allow us to determine what the N and M maximum values were. as well as the MX and the NX corresponding figures. Once these calculations had been completed, we can then design the column for one case and then cross-reference it with the other. In order to choose the design member which is under axial compression, it was required the L buckling to be calculated first. In case 1, the design member which was chosen was 150 UC 14.8, as it had the ability to hold N maximum, which was 112.629 kilonewtons. However, the first choice was not acceptable as the L buckling was not safe when buckling out of plan. So the column was changed to 150 UC 23.4. Case 2 was now calculated to determine the maximum moment force and corresponding normal face. The final calculation which was used to be completed was determining the column capacity for the combination at compression and the bending moment. However, the total was greater than 1, meaning a recalculation had to be done.
Designing the central and end rafters, we had to ensure that we calculated it correctly so that there would be no failure within the structural members. So the first step was to determine the dead and live loads that would be situated either on top of the member or beneath. This calculation was achieved when adding together the roof sheeting, ceiling weight, insulation weight, services and purlins. However, we also included the rafter weight where an assumption was made of 1. For our shed design, the total dead load of the building was 4.504 kilonewtons. The uniformly distributed action load was calculated through the equation 1.8 divided by A plus 0.12. In this case, our A factor was 6 by 6. Once this figure was achieved, we then multiplied it by 6, which gave us our Q factor of 1.5 kilonewtons per metre. However, as this was an intermediate beam, we had to add an extra 500 kilograms, 4.9 kilonewtons, as this member was to hold an engine hoist that was fixed to the midpoint of the rafter. The extra 4.9 kilonewtons, however, was not required to be added to the end rafters. Upon the completion of the wind loads and pressure forces calculations, it could then be determined what the combination of action was. For the intermediate rafters, the forces applied to the rafter was 6.841 kilonewtons, with a reversal wind action of negative 9.338 kilonewtons. For the end rafters, it was 5.4048 kilonewtons and a reversal wind action load of negative 9.338 kilonewtons. Now that this figure was determined for the load which was placed on the rafter, another equation was required to determine the overall weight that it could carry. Our design could hold 40.884 kilonewtons per metre. Therefore, using the universal beam, the next process was to determine when the bottom flange of the member was under compression. When the calculations was achieved, it was determined that the member which was chosen was too small and will not be able to hold the weight when the bottom flange was under compression. This meant a new rafter member had to be chosen, and it would be 310 UB 46.2. The final process was to determine the deflection of the beam and how much it would deflect when under maximal load. For our shed, the maximum deflection of the beam was 3.8 millimeters. The end rafter also had to be chosen, and it was 310 UB 40.4, and the maximal deflection was 4.39 millimeters. Dimensions 6 meters by 6 meters by 4.5 high. The first step was to determine the appropriate bracing that would be suitable for the building. This was calculated through determining the wind speed, with the main focus being on the ultimate limit state, which was sourced from the Australian Standards 4005 2012. Once we determined the ultimate limit state, we were able to calculate the pressure and the suction with the equation used P equals QU plus CP. Based off these calculations, the gable end surface area was calculated. However, we first had to determine the height of the opposite wall, which was 4.3 metres. Upon completion of the gable end surface area, the pressure and the suction forces that are applied to the bracing was calculated through the formula area equals P. The wind pressure is 13.78 kilonewtons and the suction pressure is negative 11.79 kilonewtons. Once the pressure and the suction loads were completed, the design force could then be calculated. Our R value was 25.57. Was to determine the force in each of the members. In this case, we'll use a calculation 2 times F1 cos of theta equals 25.57, take 11.79, take 13.78, which equals 0. Therefore, the forces that are applied in F1 equals 0 kilonewtons. As F1 had now been calculated, F2 could do the same. The equation we used was F2 plus 13.78 equals 0. Therefore, F2 equals negative 13.78 kilonewtons. The final part of designing the member was to determine the elongation of the member, where we assumed that the rectangular hollow section would be chosen. Now that the roof bracing system had been completed, the wall bracing system could then be calculated. The first step was to determine the RB value. The equation was used to determine the RB value, which is the forces that are being applied through each of the wall struts. In our design, the kilonewton factor was 36.528. Therefore, the design capacity table was used to determine what the adequate bracing member should be. The bracing member which was chosen was 50 by 50 by 3EA. The bracing system has the ability to hold 68.9 kilonewtons, which means it's safe.